Welcome to another GCBASIC tutorial for the PIC16F175 chip family. This is part 15. So part 15 is looking at a function called Millis and interrupts in the round, so an overview of them. And so please like and subscribe this video and the channel. I'm in it for the like and subscribes. I want to get to 1,000. Please like and subscribe. So part 15, Millis interrupts, very important part. Not to be afraid of them. They're very simple. So what I'm assuming is that you have installed the software, you can program this chip, you have tested that, you've got a switch attached, and you've got 4 LEDs as per the specification that I will shortly show you via suitable resistors. I'm going to be using, use my pen, I will be using the LEDs here. Oops, I'll be using the LEDs. And I think I'm going to be using the switch as well on port A. Port C, port A switches. So first of all, let's have a look at Millis. Millis is a function that is very similar to the Arduino's Millis. It actually operates the same. Some of it, I'll be honest, I just looked at their code and thought we can implement that. And it returns a number of milliseconds since the program has been started or the chip has been reset. Has a great benefit, it's running continually. But that's also a downside because it's running continually. It's interrupting the major program that's running to update the function Millis. There are no code halts. It runs in the background. It is an interrupt itself. And it's unlike delay milliseconds or wait because it is constantly running. It returns an unsigned long number equivalent to 4.3 billion milliseconds. And it's got a precision of about 1 millisecond via the timer. And these are internal clocks, so buyer beware. You know, if you can get a better clock on it, then great, but generally we're using the internal clock to get the cycles. So that gives you an approximate 50 days, 49.7 days before it resets back to zero. And it's great because it just resets back on the power cycle back to zero. So you can run the chip for nearly 50 days and keep the time pretty accurate. So what we're going to do is walk an example, but I will show you what's on the lab here. Okay, first, let's go out to desk cam. I've got my Gabtronics oscilloscope still attached. I've got 4 LEDs. I think I'm going to use one, and I've got a switch attached. And here's the chip over there. You know, we'll see it, but we're going to see it, but nothing fantastic. Okay. Let's start up the IDE GCS, and that'll bring up GC Studio and enter GC Studio. And that will then, I'll zoom in on here and then select the 16F175xx chip range demonstration. Essentially, we're in the IDE, press Control B. There's many different ways. Control B, Control B. Yeah, Control B will open it and open up 310 millis. I'm just going to purge this function key. So in here, just click function key F5.gcb, and I'm putting a filter on. I'm filtering out everything. So now I've just got 310 millis. And there we go. Here's the program. We'll take it to the top and shut down the Explorer window. Anything in green's a comment, so just leave that. Okay, what have we got? We got our standard header, which defines the chip. In actual fact, it also defines the frequency. It will always set it to the maximum frequency. Option explicit means we're going to define our variables. So let's have a look at what's going to happen. Well, I'm going to set a few things as outputs, the LEDs as outputs, and a few things as inputs. Look, you've seen all that before. This is where the program really starts. Hash include less than millis.h greater than. And that means include the library for the millisecond timings. And it will pull the whole code in for you. And that is all that you need to do. Now the function millis is available to you. And we'll look how we do that in a moment. So what I'm going to do is I'm going to flash an LED every 1000 milliseconds. Therefore, I need to look at and store the time that I'm looking at, or the number of milliseconds passed, and I'm just going to compare it, see if it's greater than 1000, and bang, job done. In actual fact, it should be 1000 or less than 1000. 999. I'll let you play with that. So I need a couple of variables, and I am going to use these two variables. I'm going to use the same program twice for the same video today. So I am going to store the current milliseconds and something called the last milliseconds. And I'm just going to compare those two in a short while. Okay. And then we're going to go, yes, has 1000 passed, do something. Set them both to 0. And that just gets the program running. And here's my main loop, do loop. It's a do loop here of do something forever. And it says here, here's the function Millis. It's as simple as that. You go Millis. You might get away without the brackets, in actual fact, or braces, but just do it for clarity. It puts the current milliseconds passed since the start in the variable called current ms, current milliseconds. And then ignoring int off and int on for a minute, it says that if the last minus taken away from the current milliseconds is greater than 1000, toggle the LED and then record the last time in the last variable. That's what it's going to do. So what about this int off and int on? That turns off the interrupt. And you need to turn off the interrupter for these few cycles. Why? Now, why? Because you need to make sure that the Millis has not incremented during the cycle itself. So what I mean by that, as it's doing its mathematics, you want to make sure you get a consistent time back. So good practice. Turn the interrupt off and turn it back on for a couple of minutes. And it's only a few cycles. You can play with this and improve the performance of it, but I'm just trying to say that's a critical process. So if I program this, we're going to see a couple of things happen. Function key F5, we'll program it. Now I've moved up the version of the program of the software look, because I've now got color coded in here. Look, it says the current version I'm using is build 540 in blue. It successfully compiled the program in green, how long it took in blue. It's assembled the program, and then it's done the programming cycle and said it's successful. So look, you can see that there's improvements happening as we speak. Things are happening. So what's happening out on webcam? Let's have a look. Oh, look at that. Something's flashing every second. Look, every 1000 milliseconds. Let's have a look at that on the oscilloscope. Now, can you see the oscilloscope? That's the question. I think you can see the oscilloscope. No, you can't see the oscilloscope. Every second. It is every second because it shows it on the on there. 1000 milliseconds is evolving. So Millis is available to you if you need it. I don't use it. I'd rather use an external clock, to be quite frank, because that's easier. But it's there. Millis is a function. You include the library and it becomes available. Back to PowerPoint. So let's look at interrupts in the RAM, because Millis is an interrupt, but we need to understand it as a whole program, as a whole thing. So interrupts are events that occur within the microcontroller that alter the normal execution flow. In our example there, Millis has been interrupted. Millis is operating at all times in that do loop. It's just carrying on. And it responds an interrupt, or the change of flow of execution, is because of an event. And it could be an internal or external event. Now, there has some advantages. It's responding to critical events, and it can make the efficient use of the resources because you don't have long-running code. You can have external interrupts in terms of the types. You can have different types on different inputs. You can have timers, you can have peripherals, you can have software. And it plays with, works with key registers like intcon, PIE1, PIE2, PIR1, PIR2. These are the peripheral interrupt flags. But a lot of this is hidden from you in GCBASIC because they're automatically controlled for you. I'll show you how. But you do need to find and define an interrupt service routine, ISR. Special function that occurs when the interrupt happens. So in Millis' case, it's calling a function to actually update the Millis counter. My advice is your ISR needs to be as short as possible and efficient as possible to avoid delaying other operations. Don't be doing long-running operations inside of Millis, inside your interrupt, because it cannot handle other interrupts whilst it's going on. And you can have many, many, many different interrupts. How many for this chip? 46 different type of interrupts. We've only looked at one, which was a timer interrupt, timer 0, overflow, number 34. That's what Milli uses. But look at all these. There's so many. And there's a list, look. Oh, there's a list. It says ADC ready, ADIE, ADIF. That is the enable bit, and that is the flag that one's occurred. These are all listed in PIC info, and we'll have a look at that in a moment. So what we're going to do, we're going to take one of these. Let me show the one that I'm going to be using. IOC, interrupt on change, interrupt on change. Where's interrupt on change? In all these here, look. Oh, port change there, look. Number 22. If the port changes, then it will set this flag, IOCIF. There's a flag been set. And how would you enable that? IOCIE. Now, to be quite frank, they are managed automatically by GCBASIC. They are there for reference, but I'm going to show you the details. So this particular one, IOC, interrupt on change, detects the change in a specific pin. How? Because we're going to tell it exactly which pin we want it to do. We have to set the port into the state that makes logical sense. So it needs to be an input. And we have to configure the correct register in the microcontroller to detect rising or falling edges. We have to define an interrupt service routine to handle that interrupt. And then you'd need to enable it. Now, some of this is all controlled within the program automatically, but I will show you. So how do I figure out whether the port that I've selected supports IOC? Well, if you look at the pin allocation table in the datasheet, it says here the capabilities of a 28-pin. This is the chip here, port A3. You can see it says it out. I'll draw an arrow to it, A3 there. IOC, top right hand corner, and it says it's called this. IOC, that's interrupt on change, AC, sorry. Oh, so sorry. IOC A3. So it tells you that it has a capability of interrupt on change. If it's not listed there, it doesn't do it. Not every port does everything, but this one does. IOC A3. And so what we're going to do is look at some code here, and we're going to actually add in just a bit of logical code here. I'll show you it here first. We're going to set the source of our interrupt. IOC, you saw that, IOC A, that's A3. I'll write that down in big letters, A3, and I want to test it when it's negative. The other option to that is positive, P, A, P3. And we're going to add in this call here, look. It says On interrupt port change, call the interrupt handler. You can call the interrupt handler almost anything that you like, really, but I just called it that for today. And in our interrupt handler, I've got a little thing running, going, oh, if the switch has been pushed, wait a few milliseconds and then inform the main loop that the switch has been pressed. In reality, that's all you need to do. You say, well, if the switch has been pressed, set a flag, and I called it SW pressed equals true, and then handle it in your main program. And this is our main program here between the do loop. It says if the switch has been pressed, then put the LED connected to RC3 to that state. Job done. Well, it's as simple as that. Let's see it working. Is the easiest way. Back to the IDE. Now, we saw the code for Millis, but tucked away inside of there, I've got some other code, because that's the way you can do it in GCBASIC. You can have lots of code. As I said, you need to enable the IOC on port A3. Said that, going negative, IOC negative, IOC AN3 is how you do it. You set it to 1. Easy. Just does it. And if that bit exists, it will set it to 1. Here is my handler. On interrupt, when the interrupter calls happens, port change, call the interrupt handler. Because the port is going to change. I want IOC A3 to be my interrupt. So I'm going to call a handler and it will make sure it's correct. And here is my handler down here. So subroutine, always has to be a subroutine, interrupt handler. I do a debounce of 10 microseconds. I take the switch state because we have a constant, remember, called port A3, and it sets the state. It sets something to true and get out of the routine. It's the fastest way I could think of doing it. This is just a little debounce thing. You might not need this. It's a debounce. So look, all it's going to do is come in. It's going to check the state, set software pressed equals true, and get out. And then in our main program up here, I've got a little, after the Millis stuff, I've got an if pressed, set RC3 to that state, and then set it to false. Oh, why have I set that to false? Because down here, I want to make sure that I don't handle it more than once. Because if true, if I set it to false, this equates to equals true. I should be put it in full really, I guess. True. So if it's true, it will toggle it. So why don't I just program that? F5, go out to deskcam. Oscilloscope stop for a few seconds because it would do, wouldn't it? And then now the oscilloscope's playing catch up. Look, there you go. You can see down there it's a different scale. My switch is here as it has been the whole time. And if I push it down, the LED comes on. There is no code that really, it's all done by the interrupt. Me pushing this raises the interrupt. And you might go, no, it doesn't. I tell you what, I'm going to add some code in just to show you. So what I'm going to do, don't do this, but it's a good way of doing some debug. Look, is that in the interrupt handler, I'm going to say pulse out. Let me just use pulse out is sort of a little underscore. It's got a little box on it, which means I can actually say, I'll say RC2. It's not good to put a big delay in here, but I'm going to do it just so you can see it on the camera. Okay, pulse out on RC2, 50 milliseconds. Reprogram it. So RC2, which is the green LED, will flash whenever I push it down. So it's just programming it. And you just saw it flash. It just flashed. And that's as it's coming into the interrupt routine. That's the interrupt routine as it flashes. And then the blue one here is in the main program. Really simple. And you can do that with all the interrupts. So let's look at all the interrupts by going function key F4, PIC, PIC info, and then we'll look out in here in PIC info. We'll zoom in. And in here, here are the full list of interrupts from ACD, ADC, right the way through to zero crossing detection. And this enable bit is set automatically for you by the onInterrupt command line. And this bit is cleared automatically for you. But in the demonstration, I did clear it for clarity and clarity only. And so you could say onInterrupt external interrupt 0, it would automatically enable it and automatically clear it after it's been gone through the interrupt routine that you've written. So port change we've had a look at, and if we look deep inside the assembly, it would be great. So whilst all this is happening, if we look back at this cam, if I'm pushing this, we still know that this LED is going to be every 1,000 milliseconds. So we've still got our 1,000 milliseconds. So we've got at least 2 interrupts running at the same time here. Not hard. onInterrupt. Let's look at the program. I'll get rid of that for us. onInterrupt. It's the very simple, the source and what routine to call. And you can have as many as you like. Just watch the performance and keep them short. Back to PowerPoint. So we'll call that a wrap. Next, we're going to be looking at the storage within the chip, program memory, SIF memory, EEPROM, and data blocks. All very simple. We're well into the end of the tutorials. And with that, enjoy.